Okay, these are some of the one theorem that we will be needing today. So your first homework is finally online after 1 month. Okay, they are due for next week, and it's from the previous chapters we had covered, so that you will be reviewing what we had done. And hopefully from now on you will get a new homework every week. Any questions about the things we had done? Did you check the homework? No, have a look so that if you have any questions we can also discuss tomorrow. I mean, do not solve them if you don't like yet, but just think about how to solve it. Now today, before we finish this canonical ensemble, the last thing we will be discussing will be paramagnetism. Well, if you remember the properties of magnetic materials, there are several mechanisms. I mean, if you have any material, put it in a magnetic field, then the material becomes magnetized. There is the paramagnetism, there is the diamagnetism. We have paramagnetic materials. Diamagnetic materials. And ferromagnetic materials. Well, in fact, to some extent, all of the mechanisms that leads to such phenomena, they exist in all the materials, actually. But depending on which one is more dominant, then you get these paramagnetic, diamagnetic, or ferromagnetic materials. Now, what happens in paramagnetic materials is that if you imagine the atoms, most of them have their own permanent dipole moment, magnetic dipole moment, which creates a magnetic field of its own. And if you put them in a magnetic field, these magnetic dipoles, just like electric dipoles, they try to align in the direction of the magnetic field. So if you have a dipole, let's say this is the magnetic dipole, and if you put it in a magnetic field, there is the potential energy, which is given by minus mu dot H or mu dot B in vacuum. So this basically tells us that the magnetic dipole moment will try to align with the external magnetic field. And this phenomena is what causes the paramagnetic property. So the magnetic dipole creates an additional magnetic field in the direction of its direction. So in such materials, when you align the magnetic moment with the magnetic dipole with the magnetic field, the total magnetic field is basically enhanced. Now, the mechanism for diamagnetic materials is slightly different. So, and the effect is also much smaller than this alignment of the magnetic dipoles. So if you have a material made up of atoms or molecules that have their own permanent dipole moment, the material becomes paramagnetic. But if it happens that the material making your system doesn't have its own, the atoms or the molecules, if they don't have their own magnetic dipole moment, in that case, this phenomena, the alignment of the dipoles, it just doesn't happen. But rather what happens is, if you, for example, imagine the electrons orbiting orbiting an atom, so let's say this is the nucleus. Let's just look at a very simple picture. Let's say there is an electron orbiting. Well, this will create a magnetic dipole moment, but keep in mind that the atom has many electrons, and when you sum them up, the total magnetic dipole moment can be 0. So we are basically looking at such a material now. If you take such a material, consider one of the electrons classically, and then put it in a magnetic field. Let's assume that here we have a region where there is a magnetic field out of the board. And of course, putting it in a magnetic field, you can do it in two ways. Either you turn on your electromagnet at the position of your atom, or you just move the atom to a region where there's a magnetic field. But both of these processes basically results in the creation of an additional EMF for the electron, and hence its motion will be modified. The effect will be the creation, the induction of an additional magnetic dipole moment, and according to the Lenz's law, delta mu is in the opposite direction. So all the electrons in an atom will acquire additional magnetic dipole moments in the opposite direction. So in the case of the paramagnetism, you basically obtain a net magnetic moment in the direction of the applied field. In the diamagnetism, you obtain an additional magnetic dipole moment in the opposite direction to the applied magnetic field. So that in diamagnetic materials, inside the material, the magnetic dipole moment is the magnetic field, the applied field, the magnitude is reduced in the sum. And then there is the ferromagnetic materials. There are not many of them. Iron is the most common example. That's basically the origin of the name also. It's a phenomenon first seen in iron. So in these materials, what happens is there is a strong interaction between the spins of the electrons making the system. So they tend to align. And due to this alignment, if you just take an iron or any ferromagnetic material, basically, the spins enhance the magnetic moments in this material, of the atoms making this material are actually aligned in the same direction. And of course, if all the atoms are aligned, that would create a huge magnetic field, but a huge magnetic field means a large energy. So to minimize the energy, what the system does is essentially you get domains, so you get regions of the material. The shape depends on the material. Basically, in this region, the magnetic dipole moments are aligned in this direction. In this region, they might be aligned in a different direction. Here, they will be aligned in a completely different direction. So basically, we have the spins are aligned in different domains so as to reduce the energy. At the same time, different domains are randomly oriented so that the total magnetic field is reduced, and hence the energy is further reduced. So this is how we basically to make a permanent magnet. What you do is you just take such a material, you put it in an external magnetic field, and this external magnetic field, basically what it does is it causes the domains which are aligned with the external field to grow. And the domains that are not aligned with the external field, they just reduce in size. So the total magnetization is enhanced. And if you will just plot the magnetization of such materials as a function of the applied field, so let's say even if you start with an unmagnetized object, you increase B, it starts to get magnetized. After some time, it becomes saturated. You cannot increase it any further. But then if you lower the external field, it doesn't follow this line. So it basically, when the B external field goes to 0, it still keeps some of its magnetization. And hence you basically have a magnet. To reduce this magnetization to 0, you need to apply a field in the opposite direction. And then after some point, it will be reduced to 0. And if you keep applying a larger external field in the opposite direction, again you will get a saturation in the opposite direction. And then you can start to lower the magnitude. Again, it doesn't go to 0, and this will be basically the plot. Well, this is called the hysteresis curve of a ferromagnet. So what it says is that the magnetization of these ferromagnetic materials doesn't depend only on the external field, but also depends on the history of your material. For example, at 0 applied external field, the magnetization can be 0, can have this value, can have the opposite value. It will depend on the history. Anyway, so our main subject here is the paramagnetism. So basically we have these magnetic dipole moments, and in fact for simplicity we can just say that, okay, let's just take the atoms, we have the electrons, we have a collection of electrons. The energy of the system will be sum of over all the electrons, or all the spins, let's say, of minus mu I dot H. Well, this is the magnetization of the material is basically defined as the mu I, the sum over the mu I, let's say the average. Now, if you remember what we do in classical, okay, so in canonical ensemble, we were looking at the partition function, which was, if the systems are not interacting, can be written as the partition function of a single particle making the system raised to the power n. And then there was the 1 over n factorial if indistinguishable particles. So if you look at our Hamiltonian, well, let me use B. Well, if you look at our Hamiltonian, well, the spins, we are assuming that they are not interacting with each other. We are ignoring the kinetic energy of the spins. And then, so we can use this expression. So for us, it's enough to calculate the partition function of one of the spins. Now Q1 will be just minus mu dot B, or minus mu B dot times the cosine theta. Sorry, this is not Q1, this is the energy. Q1 will be sum over e to the power minus beta times minus mu B cosine theta. This is the energy summed over all values of theta. Or we can convert this to an integral. This will be sum over all theta and phi. You see, we are first treating the system classically. In the classical picture, the microstate of a single spin is just given by its orientation. Its magnitude cannot change. So it's just the orientation will be changing. So this converted into an integral is just e to the power beta mu B cosine theta times sine theta d theta times d phi. We are summing over all the solid angle, all possible orientations. Well, nothing depends on phi, so it basically brings a factor to pi. The theta goes from, well, the theta integral is trivial to evaluate, so it's just minus e to the power beta mu B cosine theta. Theta starts from 0 to pi. So if you take the derivative of that function over there, we recover the integrand. Oh, sorry, divided by beta mu b. So this is equal to minus 2 pi over beta mu b times minus e to power minus beta mu b, cosine pi is minus 1, plus e to power beta mu b. Or this is 4 pi over beta mu b times sine hyperbolic beta mu times b. So we have the one particle partition function. Well, you see, we can write this as 4 pi over x times sine hyperbolic x, where x is equal to beta mu b, or mu b over kt. You see, mu b is nothing but the excitation energy of my system, well, twice mu b. The typical energy of my system will be of the order of mu b. In the quantum mechanical picture, twice mu b will be the excitation energy. But in the classical picture, the energy can take any values, but the typical energy of my magnetic moment, if it's aligned in some random direction, would be just mu b. Whereas kt is the thermal energy of the system. So the behavior of the system will be basically determined by what is the typical energy of my system compared to the thermal energy of the system. This is true in classical statistics and also in quantum statistics. In quantum statistics especially, it will be more important at low temperatures, because if the thermal energy is much lower than the excitation energy, then in the quantum system there won't be any excitation. So let's say Qn in our case is just 4 pi over x sine hyperbolic x raised to the power n. And the Helmholtz free energy, remember that was minus k t times logarithm of Qn. This is equal to minus n kt logarithm of 4 pi over x times sine hyperbolic x. Now we know the Helmholtz free energy, we can basically calculate everything. Well, let's look at the entropy. What was the entropy? In terms of the Helmholtz free energy? Well, always keep in mind these thermodynamic relationships. The U is equal to SDT, no, not SDT, TdS minus PdV plus mu dN. The U minus Ts is minus SDT minus PdV plus mu dN. A minus U minus Ts is what we call the Helmholtz free energy. So what is S in terms of the Helmholtz free energy? Yes, minus dA over dt, keeping, well, dV should be 0, V is constant, dN should be 0, N is constant. Well, in this problem, and V doesn't really play any role. We are only looking at the spin degrees of freedom. So in a sense, it's not actually moving, these spins. So we already know what A is, so if you just take the derivative, S is, let's say, the derivative of the first T, well, that is basically A over T, plus d by dt, let's say d by dx first, nkt of the logarithm of 4 pi over x sine hyperbolic x times d by dt, dx by dt, x was just beta mu b, so it's mu b over kt. So S is a over t plus nkt. Let me take this time derivative first. So that brings us a minus mu b over kt squared. Now let me take the derivative with respect to x. The derivative with respect to x will bring me, let's say, the derivative of the inside first. This is minus 4 pi over x squared sine hyperbolic x plus 4 pi over x times cosine hyperbolic x divided by 4 pi over x times sine hyperbolic x. Well, let's do some simplifications. This t will cancel this one, so what remains over here will be again just x. So S is a over t minus nkx times x over 4 pi, 1 over sine hyperbolic x, 4 pi, let me just take it, the numerator also in, let's say, let me just take out the minus 4 pi over x squared out. And what remains inside will be sine hyperbolic x plus x cosine hyperbolic x. So this 4 pi cancels this 4 pi, this x times x will cancel this x squared. So what we have is S is equal to a over t minus nk 1 over sine hyperbolic x times, well, this is a plus. Well, let me also put this inside. I have 1 plus x cotangent hyperbolic x. So this is my entropy. And keep in mind, okay, so let's just keep it in this way. If we want to calculate U is basically A plus TS. Sorry, I made a mistake above. You see, when I take the derivative of the first term over here, I get this T's drop, so I get A over T, but with a minus sign. So this is minus. This is minus. This is minus. This is minus. So U is A plus TS, which is just NKT, 1 plus x times cotangent hyperbolic x. This is the internal energy of my system. Well, let's see how it behaves at low temperature, high temperatures. So what? Now, to start with, the temperature doesn't really, okay, one behavior is the overall NKT dependence. And then the second dependence on T is through the combination X. So we can look at what is U over NKT. So this depends only on X. And keep in mind that X is mu B divided by KT. So low temperature, that's T is small, is more or less the same thing as high B. Or high temperature, T is the same as small b, small magnetization. So let's see what happens at high b. Well, before looking at that, okay, we already know U. Let's look at the magnetization of my system. What is the magnetization? Well, we had already seen what, let's see what we had done. You see, the magnetization of the system we can write as nothing but the minus the gradient of, with respect to the coordinates of B of E. So this is the magnetization. Just draw it from this relation over here. The energy is given by this expression. In our case, it will be U, the gradient with respect to B of U. This basically amounts to saying that, you see, on one hand, we know that the U is equal to TdS minus PdV minus plus mu dN. Now, if you put our system in a magnetic field, it just brings minus m dot dB. This is our du, or dA will be minus SDT minus PdV plus mu dN, again minus m dot dB. In our case, I mean, we have a fixed magnetic field. We can just choose its direction to be in the z direction, and then the magnetization will also be in the z direction only. And so mz will be just minus dA by dBz, or keeping the temperature, volume, and the number constant, or minus dA by dB. So we already know what A was. So this is our A. mz is minus dA by dB at constant all the other parameters, which is nkt, derivative of the logarithm of 4 pi over x times sine hyperbolic x with respect to x first, and then derivative of x with respect to b. And if you go back, let's not do that derivative again. We had already evaluated that derivative. You see that derivative with respect to x is already this term over here. That is our energy. Now let's write it down. So this is equal to nkt times derivative of the logarithm with respect to x is minus 4 pi over x squared sine hyperbolic x plus 4 pi over x cosine hyperbolic x divided by 4 pi over x sine hyperbolic x multiplied by dx by dB. Well, remember, x was mu b over kt, that is mu over kt. Again, let's just do the same things. This is nk, the temperatures, kt will cancel in fact. Times, let me take out that minus 4 pi over x squared out, sine hyperbolic x plus minus x times cosine hyperbolic x times x over 4 pi, and this thing divided by sine hyperbolic x. So magnetization of my system is a function of the applied field, and the temperature just turns out to be, let's say this x will cancel this one, this 4 pi's cancel, minus n times 1 over x, 1 minus x cotangent hyperbolic x, or minus n times 1 over x minus cotangent hyperbolic x. This is the magnetization of my system. And then we also know the energy of my system. Well, here I made a sign mistake. Let's see, here when I take the 4 pi over x squared out, what remains here is a minus sign. And let's see, here I have a factor mu. Well, essentially the coefficient multiplying n is just the magnetization of a single dipole. Now let's look at now we can just check the small x and high x behavior of these things. So small x, which corresponds to t goes to infinity and or b goes to 0. Both of these will result in a small x. Now, if you remember, let's look at the cotangent hyperbolic. This is e to power x plus e to power minus x divided by e to power x minus e to power minus x. Well, you see, this is just a finite number, whatever the value of x is. If it goes to infinity, then e to power x is dominate, so it becomes 1. If x goes to minus infinity, then e to power minus x is dominate in the numerator and denominator, so cotangent hyperbolic just goes to minus 1. So this cotangent hyperbolic is always in the range minus 1 and 1. Now, if you look at m, or the same thing for u, both of them has, okay, so you see, when x goes to 0, this goes to 0, the second terms. Or in m, the first term is dominant. So we have the m goes to minus n times mu. And u goes to n times k times t. Okay, so whenever you get a result, you should always think, does that make sense? Was this what you expect? Yeah, this is actually not what I expected. You see, let's just look at the spin 1/2 case. Okay. But this quantum mechanically is kind of easier to understand, let's say. Now, if the temperature is high, then the magnetic field should basically have no effect. So all the magnetic dipoles will be randomly oriented, with all orientations equally probable. Well, if they are all randomly oriented, with all directions equally probable, then the total magnetization should be 0. Because total magnetization is nothing but the sum of the magnetic dipole moments. M should be 0 in that limit. Secondly, if all of them are randomly oriented, some of them will be aligned in the direction of the applied field, some of them will be aligned in the opposite direction. And so the energies of each one of these magnetic dipoles will be, some of them will be in the same direction, some of will be positive, some of them will be negative. The sum of the energy should again be 0. You see, in this expression that we obtain, which is for me obviously wrong, so that we should go back and correct it, you see the maximum energy that a dipole can have is just mu times b. If we have n of them, the maximum energy should go to mu times b times n. But that's not what we obtain. So obviously there's something wrong. Well, let's see what might have been wrong. Maybe we took the small x limit wrong. Okay, small x cotangent hyperbolic x will be... oh, by the way, let's expand this cotangent hyperbolic. You see, at small x, this will be somewhat 1 plus x plus 1 minus x divided by 1 plus x minus 1 minus x. So this is 2 over x. So basically that was what I was wrong. The cotangent hyperbolic is not restricted to the range plus and minus 1. In fact, it is excluded from that range. So it starts at, for x is very large, it will start from 1. As x goes to 0, it will increase and diverge. So that was probably my mistake. Well, that was apparently the mistake. So let's see with this understanding what the correct answers would be. So let me erase these. These are obviously not correct. Let's start with U. U goes to nkt times 1 minus 2 over x. Oh, minus 2. Right? So this is minus nkt. Still not correct.
No, it's 2x.
Well, you see, in U, I have 1 minus x cotangent hyperbolic x. So I have...
Yeah, I think we find the wrong result here.
Here.
It's not 2 over x, it's 2 over 2x, isn't it?
Oh, you are right. This is 1 over x. So that's y minus 1, so that is 0. Well, that is what we expected. So at high temperatures, we expected the energy of my system to be 0. That is, we are on the right track. But obviously, we would like to get how it depends on how it goes to 0. Not just knowing that in the exact limit is 0. So I need the next term over there, over that expansion of cotangent hyperbolic x. So let's see. What is cotangent okay, so cotangent hyperbolic x, let's keep the x squared terms. 1 plus x squared over 2 plus 1 minus x squared over 2.
That's right.
Hmm?
It's plus x squared over 2.
Plus x squared over 2, correct. Well, let me ask, cotangent hyperbolic x, is it an odd function or an even function?
Should be odd.
It should be an odd function. So x squared terms will not contribute. Okay, I was trying to avoid to take the derivative of cotangent hyperbolic, but that will probably be the best choice.
Then just consider the third order terms.
Yeah, that's what we will take. Cotangent hyperbolic x will be approximate. This is not even a Taylor expansion. Let us take x times cotangent hyperbolic x. You see, I cannot expand cotangent hyperbolic x around x is equal to 0. It's not analytic at x is equal to 0. There's this one over x. But I can Taylor expand the x times cotangent hyperbolic x. That will be analytical at x is equal to 0. In fact, that's what I need.
By the way, second order terms will contribute.
It should not.
Yeah, but the result should be something like 1 plus x squared over x.
Okay, so?
Then, again, we will have an odd function.
But what I want is, I want the x cubed term. Well, the next term will be linear in x. And that they, let's do it. So cotangent hyperbolic x, 1 plus x squared over 2, plus 1 minus x plus x squared over 2, divided by 1 plus x squared over 2, minus 1 minus x plus x squared over 2. So let's see, in the numerator, these x terms cancel. And what remains is the same, so I can just cancel this one and here put a factor 2. In the denominator, the 1 cancels, x squared over 2's cancel, so I get I can just add this, so I get a factor 2 over here, so the 2's will also cancel. So what I end up having is 1 over x times 1 plus x squared over 2. You're right.
No, it's just x squared.
Yeah?
Oh, you had overall 2. Okay.
So cotangent hyperbolic x is, for small x, this is 1 over x times, well, okay, no. 1 over x plus x over 2. Now let's look at u. This for small x becomes nkt 1 minus, if you multiply this one by x, I get 1 plus x squared over 2. 1's cancel, so it just becomes minus nkt x squared over 2, or minus nkt over 2. X is mu b squared divided by k squared t squared. So u, t will cancel. U is, k's will cancel one of them. Minus n mu squared b squared divided by 2k t. So this is how the energy goes to 0. Now let's look at the magnetization. This was our magnetization. This for small x will become minus n mu 1 over x minus, for the cotangent hyperbolic we had obtained 1 over x plus x over 2. Well, these will cancel, so magnetization is n times mu times x over 2, or n times mu over 2. X is mu times b over kt, which is n mu over 2k, n mu squared b over 2k times 1 over t. Well, basically the magnetization of my system at very large temperatures is C over T. This is called the Curie's law. This 1 over T dependence. Well, of course, that C will depend on the type of material you have, because different type of material will have different magnetic dipole moments. And, well, basically that's it. And this is actually observed. If you in your book, there is the experimental results of plots of this mu times b. This one. Here is plotted not the magnetization, but the magnetic susceptibility, where the magnetic susceptibility is defined as the derivative of the magnetization with respect to B. Well, let's see, this is, let me just take out the B out. Yeah, this result is actually, as I said, experimentally verified. Now let's look at the quantum mechanical analog. Would you like to give a break? 5
minutes.
Let's give a 5-minute break before we start the quantum mechanical analog of this. Oh, okay, before giving a break, sorry. This is the high temperature behavior. Let's look at the low temperature and then give a break. Large X. Well, again, remember X is mu B over KT. Large X means T goes to 0 or B goes to infinity. Now, first of all, what do we expect at this limit? Well, we expect all the magnetic dipoles to be aligned in the direction of the magnetic field. So there will be a complete magnetization. So mu, the magnetization will be just n times the magnetic dipole moment of each one. This is expected. And the energy, internal energy, well, all of them are aligned in the direction of the magnetic field. So their energy, each one has an energy minus mu times B. Well, there's n of them. Just multiply by n. This is what we expect. And let's see if this expectation is justified. Well, again, let's just pick up the our expression of U and M. Well, you see, at large x, 1 over x is negligible, and cotangent hyperbolic is just 1. So M just goes to n times mu, as we expected. Again, cotangent, at large x, cotangent hyperbolic goes to 1. X is infinitely large. And so we can just ignore the 1. So this just becomes minus nkt times x, which is minus nkt times mu b over kt. So this is minus n times mu times b. So what we expected actually turns out to be correct. Now let's give a break, and then after the break we will just discuss the quantum mechanical analog.